I'm not going to screen share with you. You're going to have to flip along with the slides on your own devices because I feel like that's where this is falling apart. But the recording has the screen share, so that will work the same way. So I'll tell you what slide I'm on, and we'll get through the last 15 minutes or so of class, and we'll make it work. Okay, so I'm on the cover slide of Lecture 3. So I'm not sure if this was a conversation I had after class or during class, but the idea of when it's necessary to estimate these models a different way than you know how thus far. The transition from multi-level to the SEM world. That's what I wanted to present. A little bit about why you would do it that way, and then literally how to do it that way. Because there's some parts that are intuitive and some parts that are less intuitive. So moving to slide 2 then. Okay, we good so far? Good, all right. We're gonna see, it looks like it's still recording, so we'll find out. If the recording's broken, I'll just redo it. That's how it works. So the software framework, I will say, that I've been working in up to this point with y'all is what I would call Univariate Multilevel. So I start from the perspective of multi-level models in teaching longitudinal analysis. The reason that I start that way is because I feel like it's the easiest leap to get from a standard regression model into a multi-level model. Like that jump, the idea that you just have another kind of E in your model, to me is less of a jump than to go into like the structural equation framework, which is completely different setup, different notation, different everything. Now, that being said, there are significant limitations to estimating models this way. The biggest problem is that it's a univariate type of analysis. So even though technically it's multivariate because there are multiple observations from the same person, from the perspective of a data set, you're only allowed to predict one column at a time. Like y is a variable. Right? Like our outcome is this. The outcome is measured for multiple times, but it's this conceptually. And so a lot of the limitations of this just boil down to that. You can only predict one thing at a time. It is possible to trick univariate software into a multivariate analysis if you, what I call double stack your data. So let's say that you want to predict 2 outcomes at the same time. You can restructure your data so that both outcomes are put together into the same column. And you can use dummy codes as switches that apply to all of your fixed and random effects that turn them on for just this row or that row. The problem with doing it that way is that any associations that you want to have across outcomes, so like if I want to say, how does my random intercept for this variable relate to my random intercept for this other variable? Those associations have to be phrased as covariances. They can't be slopes. So that means you can't have unique relationships, you can't have moderation very easily, and you can't have mediation. A question, is double stacking the same concept as what's going on in the Z matrix? I'm not sure about that. I would say no, based on the way that I intend to phrase it. Double stacking is taking a data set that's already in long format and making it even longer by combining information from multiple columns into one column. We did this in, if you took the generalized class with me last year, I know a lot of you did this. We did multivariate analyses using univariate software. Remember pancakes and crepes? Remember that homework? No? You don't remember, or I'm too lagged?
I do remember, and I remember running into issues because we were removing intercepts and adding, and it made a difference, and it took me a while.
Yeah, everyone hates that homework. I decided to fire it. They're not doing it this year, so there's no more pancakes and crepes. Yeah, Nutella crepes, those are good. Yeah, well, you had lunch earlier. It's time for dessert, right? Dessert after lunch is a thing. Just ask my son. He had fruit snacks for lunch because I'm that kind of mom. I was like, I don't have time to fight with you about this, kid. You want fruit snacks for lunch? Fine. Yes, but the idea of like tricking software into doing these models means you don't have all of your usual options available, so it's not good. Yes, post lunch chocolate, excellent. I like that too. The other issue then, I would say that for the same reason, only having one column, so I'm still on slide 2 here, is what you're forced to do to time varying predictors to be able to partition their sources of variation. So we started talking about this with the cohort thing, right? Like if you have time varying age is both cohort and time like put into one variable. And to be able to look at those two pieces of it, we had to literally make new predictors, one for cohort and one for time, and then give each of those predictors a fixed effect in the model. That's less than ideal. It's fine to do it for cohort because cohort could never be an outcome. But when we move to time varying predictors that have both between and within variation, it would be more ideal to let the model distinguish those sources than to do it with observed variables. So it's another limitation of this univariate approach. Okay, 132, hanging in there. Switching to slide 3. So you need what I would call, in a generic sense, a multivariate longitudinal model, where multivariate means you are predicting multiple outcomes, multiple columns in your data set at the same time. You need to do that if you want to use and here's several examples, if you want to use your random effects as a predictor of something else. So let's say that I have a research question that children's differences in reading growth during elementary school are eventually going to relate to their high school outcomes, right? I might have something like that. Or students who have this pattern of growth might be more likely to graduate college than students of this pattern of growth, something like that. In that problem, I would be thinking about random slopes as the predictor variable of something else. Right? In that story, I want to see how individual differences in change during elementary school relate to some box that's measured later. Now think about how you would do that using R, Elmer, Stata, Mixed, or any of those packages. There's no way. Because in everything that we do, individual differences is an outcome of something else. It's never a predictor. Now you could put the eventual outcome in as a predictor and have like Y predict X, but that's a little bit weird. Less than ideal. So if you're conceptualizing your growth curve as the predictor of other stuff, then you need to move out of a univariate framework into a multivariate framework. To examine relationships between time-varying predictors and outcomes, like if the random intercept of this variable relates to the random intercept of another variable, for instance, you need a multivariate framework. Question. I see the hand raised.
So in this case, this is similar to the things that we did last year in PLM in path analysis?
Yes, that's where we're headed. So we're heading into a path analysis kind of world with the growth curves. That's where we're headed. So I call it multivariate longitudinal because that's sort of the most general way to think about it. Like you are predicting multiple longitudinal outcomes at the same time. They can be predictors or outcomes because you're predicting multiple columns of a data set. Another reason why you would want to do this, even if the model that you're interested in could be fit in Elmer or Mixed, missing predictors. We just talked about this. What happens to cases with missing predictors in these mixed model software packages? If I have a missing time varying predictor, yeah, they're gone. Missing time varying predictor will kill that occasion. A missing time invariant level 2 predictor will kill that whole person from my model. It will gone. There's nothing you can do about that because the outcome is like the model is trying to figure out the likelihood of y given x. You have to have the x's to figure out what the predicted y is going to be. If you are willing to believe in a couple of assumptions about your missing data, that it's missing at random, and you're willing to accept distributional assumptions about your variable, you can tell the software to pretend it's an outcome so that you can have missing cases on it. This is the process that I refer to as bringing the predictor into the likelihood. So in path models, again, drawing that analogy, we did this by saying, hey, can you estimate the variance and the mean for x along with all the stuff for y? Then that makes it so x can have missing information. X is then an outcome from the perspective of estimation. So that would be a big one. And greatly of interest to a lot of folks in this program, the last one on slide 3, to model change over time in latent variables. So it was particularly, what's the word I want? Somewhere between uncomfortable and hypocritical to me last fall, because I was teaching longitudinal analysis at the same time I was teaching SEM. And everything in longitudinal was just like, here's my observed measure, here's my sum score, we're going to fit a growth curve model to my sum score, it's totes fine. And then like I'd get to SEM and I'd be like, what? You can't just add shit up, you have to have a latent variable, what are you doing? I was right in both cases, and so, but I can't get to everything in one class, right? So now's the point where we can potentially put it together. Yes, you should not just add items up and call it a sum score. You should have a latent variable. And how do you measure growth in a latent variable over time? Well, you have to have the growth model operating on the measurement model, what is known as a second order model. It's a higher order growth model or a second order growth model. You would think the phrase latent growth model would mean that, but it doesn't. Latent growth model means I used an observed variable in an SEM package. That is what that means. So that's one of the examples that I want to show you is how to actually measure change in a latent variable. The trick with that, though, is that you have to have at least some overlap of the measures across occasions. They don't have to be exactly the same, but they have to have overlap. And you have to be able to demonstrate at least partial longitudinal invariance of the measurement model. So the way that the items relate to their trait needs to be at least mostly the same across time in order for you to say that it is the same factor at each occasion. Because if it's not the same factor at each occasion, who cares if it grows? It's not the same thing. That doesn't make sense. So to do anything in latent space, then we need to be in a multivariate framework as well. So those designs are known as either linking designs, vertical equating, vertical scaling. Those are words that people use for these things to try and estimate growth on something that where the measure itself changes over time. Trying to think of other phrases for that. So yeah, to address measurement issues at the same time that you're addressing longitudinal issues, you have to be in a multivariate framework that involves SEM. So those are my motivating factors. One more piece here and then I'll let you go for the day. Slide 4. Your choices in heading into this world of multivariate longitudinal models are known as MSEM or SEM. So there's multi-level structural equation models, as it is known, or just regular structural equation models, and by that they mean single level. So they don't use the term single level. That's me adding that on to be clear, but that's what it is. And the big difference between these two ways of approaching a problem is your data structure. Multi-level SEM is path models on long data. Regular flavor SEM is path models on wide data. So if you can maintain that basic distinction, then a lot of what follows is going to be clearer. I think that multi-level SEM has gotten a hell of a sales pitch because it sounds really fancy, but people use that term even for models that are not true structural equation models. Like if there's not a measurement model involved where we have items as indicators of a latent variable, to me it is not SEM. Like you just shouldn't use those words, but people do it anyway. So along the same lines as, you know, at the beginning of the longitudinal class, I told you if you want to sound fancy, you can start saying things like, I'm going to examine inter-individual differences and intra-individual variation. Like you can start saying crap like that if you want to sound fancy. Say you're going to do it in a multi-level structural equation model too. Boom. Then you're the height of fancy and sophisticated. Even if you don't have a measurement model. It's because random effects, when you estimate the model this way, are phrased as latent variables. That's why people call it multi-level SEM. It's not really SEM though, but it could be. A few of you have asked me questions about, say, I want to do a longitudinal analysis, but I have children who are nested in schools. Can I do that? That's multi-level SEM. Like when you would have a level 1 child model and a level 2 school model, and you could have things growing in both of those, that to me is true multi-level SEM. Multi-level SEM has fewer software options available for it. Levon basically cannot do this in R. There are other R packages that are better. I don't know how to use them, and so I cannot help you there. OpenMX or Bayesian, it's BRMS is the package. Stata does allow this to some extent. I am less familiar with how to do things in Stata, but I believe that they have generalized models available and random slopes of variable, all the things that M+ would have. M+ is what I'm going to teach you. It is continually being updated with new advances. It is user-friendly from the perspective of just getting started. It has its problems, but I feel like it's a good way to wade into this world. By the way, if you've heard the phrase dynamic structural equation models, that's just multi-level SEM with extra things that you can add. Like you can just place like an extra order, you know, for extra types of parameters. But it's a sales pitch, to be fair. In contrast, SEM is single level analysis because you're back to wide data, and there are a lot more types of SEM programs available. Not all of them will be appropriate for longitudinal analysis though, because most of them don't include ways to introduce a time or a person specific Z matrix. So the idea of unbalanced time, most SEM packages do not have a way to address that. M+ is an exception because it has t-scores. So that's the reason why I'm sticking with that as well. So that's my sales pitch. Do you feel like this is going to be useful to learn how to do multivariate stuff? I think it is. But in the same way that you got to walk before, or you got to crawl before you can walk, and you got to be able to hold your head up before you can crawl. Like getting started with univariate models, I think, is a logical prerequisite before you try to do a multi-level SEM. Okay, 144, we made it. Huzzah. And Zoom only froze like 18 times. I view that as a victory. Questions before we call it a week?
I have one more quick question.
Okay.
Kind of going back to question 10 on the homework. Are time invariant predictors always level 2 predictors?
As far as we know, yes.
Okay.
It depends on your sampling design, what your levels are. There's no guarantee that level 2 will always be persons, but in the designs we're talking about where occasions are treated as nested in persons, then yes, time invariant predictors will always be level 2.
Okay. Yeah, that makes sense. Thank you.
Sure. Anything else before we adjourn for the week? Nope. Okay, then thank you for being here and thank you for your patience in dealing with the technology issues. Homework 2 is due Monday, I think. Let me know if you need any help with that. Otherwise, have good weekends and hopefully we'll be back on campus on Tuesday. Bye for now. Thank you.